So to continue from my previous video, again, we'll start with this first table. And just to review, the peaks at 2995 and 1700 correspond to a stretch between a carbon and a hydrogen, and a double bond stretch between a carbon and an oxygen, likely pointing to a ketone or aldehyde. For the second table, we can see 7 unique carbon environments. First, 0 to 50 ppm would be the 16, 19, and 40, corresponding to a single bond between 2 carbons and an oxygen. Then between 50 to 150, we see 129, 132, and 138, corresponding to double bonds between carbons, likely pointing to alkenes or aromatic rings. And then at 200 ppm, we see a double bond between a carbon and an oxygen, likely pointing to an aldehyde or a ketone. However, if the chemical shift is above 200 ppm, this usually corresponds to an aldehyde. So because ours is at 200 or just under, this is likely pointing to a ketone. In addition, an aldehyde usually corresponds to a 9, in the range between 9 to 10 on the next graph. This graph for the chemical shift, and we can see there's no peak between 9 and 10. So we can also confirm it's a ketone. All right. And then this last graph, as I just mentioned, corresponds to the third graph, or this last table corresponds to the third graph. So we can see chemical shifts at 0.9, corresponding to 3 protons and a multiplicity of a triplet. And then a next chemical shift at 1.9 ppm with 2 protons and a multiplicity of a sextet. And these two are likely corresponding to a propyl group. And then the third chemical shift is at 2.9 ppm, which shows 2 protons and a triplet multiplicity, likely referring to a benzene ring. And then the next 2 chemical shifts are very close to each other at 7.5 and 8.0 ppm, likely corresponding to 3 protons and 2 protons respectively, and multiplicity corresponding to aromatic protons. And we can see here this first row likely shows a terminal methyl group, which we can see in the proposed structure below. Then we have the sextet, which shows another CH2 group, likely here, between the CH3 and then the next CHC group. And then we can also see a aromatic ring or benzene ring with the aromatic protons here in the proposed group. And we can also see these propyl groups coming off of the ring. And we can also confirm the benzene ring through these 3 unique environments between 129 and 138 that correspond to aromatic rings. And the alkyl chain between, we can see here for the chemical shifts, these 2 first rows. And again, I have the molecular formula at the top, C9H10 oxygen, propiophenone, and then I also did the formula here, corresponding to 5, as it was earlier.